The focus of this lesson is going to be on reliability. Previously, we defined different types of reliability and specifically defined reliability as the reproducibility, specifically of the instruments. For this lesson, we're going to go beyond that a little bit and look at how the math is done, not so that we become experts in how to calculate reliability, but more so we have a better understanding of what we need to be looking for when we're evaluating articles for their described reliability for the instruments that they used, as well as how those reliability measures are calculated for the purpose of understanding what those differences in reliability statistics and differences in reliability between measures actually means, so we have a better ability then to critically appraise the information that we're reading to decide whether or not the instrumentation and the procedures are sufficiently reliable for helping us answer our clinically relevant question. So for our key points and objectives, we need to start by understanding the role of reliability and how we have to have reliable instrumentation and procedures in order to describe differences according to the construct of interest opposed to just normal variability within the instrumentation or within the procedure. So we need to understand that without the sufficient reliability within the procedure and the instrumentation, it becomes more likely that possible differences seen between groups is a result of that variation opposed to the actual differences. We'll also talk a little bit about the differences between reliability between raters and within the instrumentation itself. And then we'll spend a decent amount of time looking at these intra-class correlation coefficients, or ICCs, and kappa statistics. So to remind you on some of the definitions, intra-rater reliability is defined as the consistency of one rater across multiple trials. And so it's the single rater, and basically intra-rater reliability has more to do with how that one rater goes about doing things, and will often correlate more with the reliability of the instrument itself. Intra-rater reliability is the consistency of data recorded by multiple raters. And so intra-rater reliability is between different raters. And so this often has to do with the strength of the procedure itself. And the intra-class correlation coefficient is the statistic that's going to be most commonly used to define reliability. And this is going to define reliability in ratio and interval data sets. So when we look at intra-class coefficient or correlation coefficients, or ICCs, the important thing to understand is that ICC is a classification of reliability measures. There's actually different types of ICC statistics that will get run. And the way that these described is you'll see the first value of the ICC being the model, and then the second value being the form of that model that was used. And so the easiest way to understand this is to look at them in how they're used. So there are three most common ICC models that we're going to describe here. And so you can see at the top there you have ICC 1, 1. What that means is it's the ICC model 1, and the comma 1 means that you're looking at a single measure opposed to an average of measure. So the difference between the forms with that is going to either be a 1 or a K. K means that we're using an average of the rater's measurements compared to the single measurement. And so the idea with that would be is if we have a rater or set of raters, as is the case with these different models, if we have them perform the test a single time and use that measure, or even just have them do it multiple times but keep each measure as a single data point, that would be a model 1. Whereas if we had them take it multiple times and then use their average, basically the idea that is, if I'm taking an individual's range of motion, so to speak, and I measure it 3 times, do I take the value that I get each time or whichever one that is most likely? So let's say I measure dorsiflexion as 10 degrees, 8 degrees, and 7 degrees. Right? So I could either take that and say that the range of motion is probably closer to 8 degrees, kind of the middle number, or I could take the average of that. And so there's value to each type of measurement. The value of taking an actual or a middle or median type approach with that, or even sometimes you will have individuals or procedures where they'll take something like range of motion until they get the same measurement more than once. And the value of that is that you're actually describing their range of motion as something that you have actually seen or measured. Whereas if you take the average, you have the ability to account for all of these different things and describe them a little bit better, from the standpoint that if their range of motion is 10 and then 8 and then 7, right, you have to account for that 10 somehow as being extra high compared to the 7 and 8. And so an average would account for that larger difference that you might have been seeing, because we know that by testing humans that everything's not exactly perfect, that the air within the goniometer itself is very low. The actual air comes from the amount of force that you might exert while doing your range of motion assessment, the amount of relaxation the subject has during that point in time, or just actual changes and differences within the tissue that occurs. And so by using an average, you allow for all of that to kind of average itself out. But the main problem with that is the average is actually a measure that was never actually seen. So you may never have the range of motion in an average be actually what you measured one time. So that's a disadvantage. In fact, if you're going to say that their range of motion is a number that you actually never measured, that can become problematic as well. But like I said, value to both aspects, but that's why we have the two different forms, 1 and K. For model 1 then, you can see this is probably the least common, because in model 1 you're going to have different testers testing different subjects, and so it's very much more a sampling type method where you're trying to use a whole bunch of different testers, and each tester may only test one individual, and then that would be it. And so you see not as common as model 2, which is probably the most common, and this is our most common between testers type mode, where you're going to end up having all of the subjects tested by the same raters. So opposed to having in Model 1 different subjects and different testers, we have all of the subjects tested by at least 2 different testers, and we're going to compare those measures between the testers. And so, and then the last one, Model 3, is the single rater, where it's the intra-rater reliability measures, where you have one rater and multiple subjects. And so you can see how these are calculated. Basically, it is the differences that you see, so the between mean squares minus the errors that are associated with that, right? And then divided by basically how we would standardize standardize the measurement without the errors. And so it's going to end up being seen as somewhat of a percentage, so to speak. It's more complicated than percentage, but it comes out to a similar sort of number. And so it looks like a percentage. It's not a percentage, but it's easiest to think of it as somewhat of a percentage of agreement, because the percentage of agreement is really percentage of the agreement when you consider the error involved as well. And so the numbers that you then go about calculating, there are different interpretation guidelines that are presented in the literature. And you can see 2 of them listed there. But basically, what you're looking for is as high of a ICC value as possible. Now, this is where your interpretation and your clinical expertise becomes important, because the value and the need for a high reliability is going to be very different based on the stability of the instrumentation being used, as well as the assessment being done. So for example, if we're testing something that is very fluid within the individual itself, talking about something like, mental processing, different aspects like that. There are so many factors that are associated with change in processing that you then need to account for the fact that that will probably have a lower reliability score. And this is one of the big problems associated with concussion neuropsych testing or neurocognitive testing, is that the reliability of those measures are relatively low when you consider them to these charts, but yet we're trying to use them to detect differences across time. And the problem legitimately is that using these neurocognitive tests or neuropsych tests, we expect a high degree of fluctuation within the individual based on all sorts of different things that are occurring. Things like sleep or fatigue or time of day. All of these things affect our cognitive ability. But then we're trying to make decisions based on one test that may have been done, a year or multiple years ago. And so that's where we have to really understand the reliability and what the tests are really telling us compared to what we might hope that they could do. And that's why neurocognitive testing is just one portion of it, but is not considered to be the end-all be-all. We can't legitimately just say people do not have a concussion because their neurocognitive tests were similar as they were at baseline. It could be due to a whole bunch of different reasons, but it's one of those that if they are not the same, then we, out of an abundance of caution, are going to say that they are not asymptomatic, even though those same differences might occur in the opposite way, where they could be processing at the same speed, regardless of their concussion, but the difference is due to something else, either fatigue or time of day or distraction level or anything like that. And so that's where we have these values and these guidelines, but we really have to understand that what does that increased variability within the measure itself mean regarding our clinically relevant question. So moving beyond kind of the procedures now to instrumentation reliability, we have the test-retest reliability, which is very similar now to our intra-rater reliability, where we're testing the same individual multiple times. But in this case, we don't have a tester, we simply have the instrument. And so we're looking for the consistency of that instrument over time. So like our neuropsych test would be an example of test-retest reliability opposed to intra-rater reliability. We also have internal consistency, which is now is more for survey type research, where we're looking at the consistency of responses to similar questions, where we might have two or more questions assessing the same construct, and we would expect similar answers and similar responses for each one of those questions. And the more similar those are, the higher the internal consistency would be. And so when we get into instrumentation reliability and this specific thing, we can continue to use ICCs, usually Model 3, Form 1, or we can also add this idea of percent agreement when we get into more nominal type data. So what percent agreement does is it's the simplest form of reliability assessment, and basically what we're going to do is, opposed to assessing actual ratio data or interval data, we're going to take the data and turn it into a nominal data set. And if you remember, nominal data set is simply a naming data set. And in this case, for the example that's provided there, we have two different raters, but opposed to asking them to actually measure the range of motion that they are finding, they're being asked to classify whether or not that range of motion is within normal limits or is not within normal limits or abnormal. And so the idea here then is we're going to try to see, based on this procedure, whether or not we can adequately classify individuals. And so this becomes more important when we're not specifically looking for things for the purpose of research, where we really need to know the exact numerical values, but instead we're trying to classify individuals as deficient in some way. So if we use the same sort of example from the neuropsych testing, we're not really concerned with the exact number concerning the neuropsych or neurocognitive testing, but whether or not the neuropsych or neurocognitive test was able to classify individuals as concussed or not, or asymptomatic or not. And so we could use something like a percent agreement here. And usually to get these percent agreements, you do a standard 2x2 contingency table, which is listed there. And so if you see, and as how you interpret this is rater 1, this is rater 2 here. And so if rater 1 classified them as within normal limits and rater 2 classified them as in with normal limits, we have agreement, right? And so these red are agreements. Basically, this means that they agree. Not within normal limits, not within normal limits. These numbers here in black are the disagreements, right? Where rater 1 said these were not in normal limits, where Rater 2 then said they were. And so if we considered each one of these an individual, we would then be able to see that 60 plus 15 is 75, right, out of 100 different things, or we have 75% agreement. And so in this case, we could just simply define this as a 75% agreement between these two testers in classifying individuals as normal range of motion or abnormal range of motion. We can then continue on if we need to and get more statistically based regarding how we can go about classifying these, and that is then the kappa statistic. And this is now the ability to statistically analyze that agreement beyond simple frameworks there. And so it's kappa statistics fall between -1 and 1, but most of them are between 0 and 1. You can think of them fairly similarly as your ICCs. Again, they're more complex than true percentages, but if you think of them as percentages, or you think about those numbers similar to how you think about percentages, where 1 is total agreement and 0 is complete absence of agreement, you can at least get closer with that. You also have a weighted kappa statistic, where in the case previously we had 2 categories, but if we had 3 categories then, where we could classify them into normal range of motion, slightly abnormal range of motion, or severely abnormal range of motion. We can continue to look at how well they agree, but in this case, if one individual classifies them as normal and another one says they're significantly abnormal, then that should count more against the reliability of that instrument because they were so far off, and that's what a weighted kappa statistic does. And so you can see the kappa coefficient values listed there, just another chart that you can use to help evaluate these kappa coefficient levels. And so you can see how, as you go through with that, in this case, because they can go all the way down to -1, you see poor agreement being below 0. And so even though you have like 0.2 to 0.4 being low, we still classify that as a fair amount of agreement because it's on that scale of 1 to -1. So to wrap up, the importance of reliability is to make sure the data is consistent, and if the data that we are getting from the procedure or from the instrument is not consistent, then we can't equate differences between groups solely to the construct of interest. So we have, and then reliability is rater reliability or instrument reliability. And we talked about how we have the intra and inter-rater reliability, and then we have test-retest reliability, and then internal consistency, as well as percent agreement as far as instrument reliability. And then the intra-class coefficient is the statistic that is most commonly used to describe these amounts of agreement, and there are different models and forms that can be used for those depending on how the testing was done, and so the math changes slightly to reflect the amount of chance error associated with different models. And then we also look at the different forms on whether it's single measure or average of measures. And then we can compare those to the charts associated to what is an appropriate amount of agreement or reliability for the measure that we're using. I understand that there are specific charts, but we also need to then analyze that compared to the standards within each one of those sorts of fields. And then the kappa statistic is a way for us to go beyond percent agreement in more nominal data sets and to assess that percent agreement mathematically to warrant out the percent chance agreement, where there's just always a percent of chance that the agreement between the two raters wasn't because they actually agreed, but just because of chance.